Thank you. It's a great honor for me to be here today at the celebration for Alan. We haven't perhaps worked together quite as much as we could have done over the years, Alan. There's always time. We're still young, so there's still time. And I have some ideas at the end, perhaps. I'd like in my talk just to mention some of the progress we have made, and my thanks go to the people that I've worked with. Giulio, who's here somewhere, I think. Oh, at the back there. The Chianti team, the UK APAP team, which is an atomic physics team, and of course the Soho and Hinode teams. So I wanted to, where should I start in such a sort of overview, a quick flight? I thought I'd start with a paper that Alan and I wrote in 1982. I thought it was a very good paper, Alan. Unfortunately, it was published in rather an obscure book, so I'm not sure it actually ever got the 500 citations or more it deserved. But I thought I'd start with it. It was a paper we did together. I was very grateful for Alan. I was relatively young at the time, but I was very grateful for the support that he gave me as a younger person, not just in asking me to do this review with him, but also in including me on, I think, the Royal Society Committee and other things. I think it's really important that I had that support. It meant a lot to me. So this is the figure 1 of the paper, which is much reproduced elsewhere, but not necessarily referenced. Sadly, it's not actually true, but this is a representation we have for the solar atmosphere and the solar transition region as a plane parallel. I wish we'd kind of charge people to use this figure, because I think we'd be relatively rich by now. However, even richer, probably Alan would be a millionaire for the number of times this figure's been reproduced. And of course, this much better represents the nature of the transition region. I sadly wasn't part of that particular piece of work. But as we can see, the transition region is quite a complex structure. Basically, I'm not even sure we've quite resolved it yet. We heard about the work on the early work on Skylab with the Harvard instruments, which showed the structure of the transition region as you go up in temperature. Of course, on SOHO, we had the SUMA instrument and the CDS instrument, and we were able to see again the structure of the as we go up through the transition region into the corona. I think that was a very fruitful time for many of us, able to work on SOHO. We had many team meetings, both SUMA and CDS, which I personally very much enjoyed. I think they even started before we'd got any results, which was even more enjoyable. But when we actually got the results, we were hosted here at MEDOC, and I think perhaps there'll be a few words about that later on. And I was on the science committee for MEDOC, and I think, again, that was very fruitful. We had a lot of workshops here. So this is just a SUMA spectrum here as an illustration. And I won't go into all of the details of the SUMA results. Obviously, Alan made a major contribution looking at the temperature gradient by combining the lines from both CDS and SUMA, which I think was quite difficult to do because of the calibration issues. You can use diagnostics, flows, line widths, electron densities, and at the top there maybe a paper that Don led, which I was on as well. We did the observations together to look at the source of the solar wind. So this is a little bit more complicated now. This is what we think perhaps the transition region looks like now, and I quite frankly have got lost somewhere in the blue and the red, but it is much more complicated. I think I in some ways preferred the somewhat simpler version, but we need still to look at the structures. With SUMA, we were able to see these low-lying cool loops in the transition region. And I think it's clear that not all of the transition region is necessarily connected up into the corona. So Do we have any hope of trying to deconvolve this very complicated region? Well, possibly. There's a solar instrument going up very soon, I think, in June. I'm not quite sure what the date is now, called IRIS, which will hopefully look in detail at the structure for up through the chromosphere into the transition region. And potentially by combining theoretical models and observations, we might be able to make progress with further progress, I should say, with the nature of the transition region. So I'm going to return again. Somebody has already mentioned the eclipse observations. I myself worked on eclipse observations for my thesis. I worked on the 1952 eclipse, which I was just about around, but probably not analyzing data at that time. And of course, it was in 1970 that I was working at University College. And Mike Seaton, my supervisor, gave me a paper by L.A. Evans and Orrell, which was on the visible lines from the eclipse, and said, right, this is for you to work on. And at that time, there was practically virtually no atomic data available for the coronal visible lines. So that was my project for my thesis, and actually that's been my project for my life because we're still working on those ions. And of course, some very good data from the 1970 eclipse was able to look at the forbidden transitions and identify some of the forbidden transitions from the ion lines and other ions. CDS played an important role for me, as I've mentioned SOHO already. Richard is here, the PI from CDS, and I think CDS was very important, particularly in the UK, for stimulating areas of research in solar physics. And we were able to look at the temperature structure up through up through the low temperatures, up through the transition region and up into the corona with a spectrometer. So the next figure from Gabriel and Mason was the density diagnostic figure. Again, this is used quite frequently, even though people don't necessarily know where it's come from. And we looked at the diagnostic ratios for different types of atomic transitions, forbidden lines, allowed lines, other types of transitions. And we showed that the ratios of these transitions can be used to determine electron density independent of many other assumptions, such as ionization, equilibrium, elemental abundances. And I use this for CDS as the electron density map for CDS here from some of the ratios from the CDS lines. I worked quite a bit with Dave Pike at the Rutherford lab, but with the whole CDS team. So some interesting work. This is an active region on the edge of the sun, and we're able to get the density and temperature structure for the active region. Moving on a little bit, I've been working more recently with the Hinode instrument, Hinode ICE team, with the PI group at the MSSL laboratory, Len Calhane and then Louise Hara. And we can see with Hinode the EUV imaging spectrometer, there is a whole host of ion lines reappearing here at 170 to 280 angstroms. And we're able to use these lines for diagnostic purposes. For example, here we have a density ratio for ion 13. Again, using the ratios, the log of density, we can see that as the ratio of the 203 to the 202 line changes, then we're able to get an electron density. And here we have an electron density map for an active region. So very fruitful collaborations in that regard. This is one of my students, Brendan O'Dwyer, who looked again at a limb observation and was able to get not only a density map, but a temperature map from ion 16 to 15. I noticed that again, we looked at differential emission measure, and in the early days, I guess Alan was quite interested in that. And I found a letter to Nature that he'd written in support of, I think, solar X-ray instruments. In fact, there was a paper by Ian Craig and John Brown which kind of really said that the X-ray instruments were no good, couldn't give you really any results. I think that Alan defended that quite vigorously, but also pointed out that you shouldn't put you shouldn't put emission measure analysis, push them too hard. There is a limit to the information that you can get out of them in regard to the width of the GFT function. I think that we're still arguing about differential emission measures. We're still arguing about different methods for deriving them. We're still trying to use them. I'm not convinced we've necessarily got it right. But there are predictions from the theoretical models as to the slope of the differential emission measure and the emission measure, depending on whether we have impulsive heating or steady heating. So we are trying quite desperately, in some regards, to use the emission measures to try and say something about the heating again for active region loops. In this regard, there is some issues about the errors of the methods and the errors of the atomic data, so which I'll come back to. I wanted to mention Chianti because Chianti, again, has been a key collaboration, and I think a very fruitful collaboration. It was started between myself, Ken Deere, and Brunella Monsignori-Foissi, who's sadly no longer with us, but it was the three of us that started the Chianti project one day in I think, in a nice seaside place in the warm sunshine. We had this good idea. And it has been very successful, and of course now the Chianti team has expanded to Giulio, Enrico, Peter, Massimo is not working with us anymore, but was for a time. And what we try to do is to make this data freely available to the community for the analysis of the solar observations. It was first released in 1996, and the latest release actually is version 7.1, this year. A complete coverage of the X-ray and the UV with over 1,000 citations. And in order to provide this, we really need to look at the data in detail. Here's a comparison between version 6 and version 7.1 compared with the Chandra spectrum from Procyon. You can see we're making great progress. It's quite often the observations that drive the atomic data, and we've made a lot of progress. We've also been trying to understand the response of the SDO-AIA channels, and I think Giulio might mention that. He's done a lot of work on that a little bit later. However, I said I'd spent my life working on the iron irons, and indeed that is true. And this has been driven by the computing power that we had. In the olden days, something that probably took me, I don't know, several days, 100 minutes of computing time now probably takes a couple of seconds on a mobile phone. And in addition, I got quite fit, I suppose, carrying boxes of thousands of cards up and down the stairs, 3 flights of stairs at University College. And there was a limit to the target that we could include, and that the limited target can affect the atomic physics. And also the sophistication of the calculations. Jack has mentioned they were developed at University College London. We had a structure, distorted wave. We had at Queen's University Belfast, we work with their R matrix. So what's happened that we're able to now provide much more accurate calculations is we've developed these codes further, and we're using them for bigger targets. In bigger cases, we're using the R matrix for the low levels, and the distorted wave for the high levels. And this is what the iron 12 target looks like now, with all the configurations we've included to get it accurate, and realizing that some of the configurations are quite important. This work has been done together with what we call the UK APAP team, and that's Nigel Badnell and Pete Storey, myself and Giulio. We've heard mention, and I won't go in details, of this is from our paper again. We discussed in Figure 8, we discussed the solar maximum and the satellite lines, and we've heard a lot of discussion. I won't go in details on that. But I just wanted to mention that, as Jack has mentioned, the work with the French colleagues was very important in that, and if I did anything in introducing Alan to my French colleagues, Jacques, my French brother, and Françoise, my French sister, then I'm very pleased that that collaboration has been very fruitful. In addition to that, I think we've already seen this photo. Alan Burgess was very key in the calculations for dielectronic recombination, and Nigel, who was his student. And of course, when I moved from University College, I moved to the University of Cambridge into Alan Burgess's group, and Nigel was there working with us as well and has continued to work with us. Sadly, Alan's no longer with us. So I think I'm nearing the end here. As I say, other people have covered this work quite well. So I just wanted to end up and say thank you to Alan for inspiring me in the first place, for working with me, for supporting me. And I have to say, at times of crisis, I do sometimes turn to my colleagues, and Alan has been one of the people I have turned to and has supported me. So I think we don't necessarily, we're getting to a stage now where it's almost difficult to remember our own names, but don't necessarily remember all the details of the atomic calculations, but I think we can still appreciate a good glass of wine. So thank you, Alan.